طيب بسم الله الرحمن الرحيم. So we in chapter 4, just to remind you, we have focused on digital transmission, where we transfer the digital signal as is. So we convert the bits into a digital signal, and then we transfer the digital signal as is. And for that, we use line coding techniques. And for line coding techniques, we have talked about 5 different categories. We've talked about unipolar, we've talked about polar, we've talked about bipolar, multi-level, and multi-transition. So this table kind of summarizes all the practical bandwidth for all the methods that we have studied. And as I said, for some methods, like for example here, for 8B6T, for 4G PAM 5, for MLT, for multi-transition, for these schemes, you will notice that the C, the case factor, is not exactly half. It's actually less than half. Okay? And as we said, practically and very commonly, the case factor is in fact half. However, for some specific schemes, we see that using specific mechanisms, like for example, the concept of inversion or the concept of multi-transition and so on, we are able to reduce the case factor below half. However, of course, for us, we don't have to memorize this in any way because the case factor is going to be given to you. Type. So these are the coding techniques. So now we talk about the concept of block coding. So block coding is actually a complementary mechanism to line coding. So it's not meant to be a replacement for line coding techniques. In other words, in practice, what we do is that we do the block coding, and then we do line coding at the sender side, and then we transfer the digital signal. And then at the receiver side, what we do is that first we do the line decoding and then the block decoding. Okay, so that's what we normally do. So block coding is a complementary thing to line coding. So what is the purpose of block coding? Block coding talks about the fact that, as we said before, the main problem for line coding techniques is when we have a constant voltage level for a long duration of time. This causes lots of problems, including the baseline wandering, the DC component, and the lack of self-synchronization. So block coding says, okay, so if you have the same voltage level for a specific duration of time, we will enforce a prior stage that will, in fact, stop this constant voltage from being there for a long period of time. In other words, we will try to avoid that constant voltage for a long period of time. So in order for us to do that, we will try to avoid the consecutive ones and the consecutive zeros, specifically for line coding schemes that use the same voltage level for 0 and the same voltage level for 1. So in block coding, we will represent each n bits from the input bits to m bits such that m is greater than n. Okay, so so in other words, if I have مثلا 4 zeros, 4 zeros could potentially cause the problem that we're talking about, that we have long stream of zeros, and this may actually cause some problems. So instead of 4 zeros, we will represent them by مثلا 5 bits, such that and we don't have all the 5 bits as 0. Okay. Of course, we have to do the reverse operation at the receiver side. So this way, if we represent each n bits with consecutive ones or consecutive zeros to m bits such that they are not consecutive ones or consecutive zeros, then we avoid the problem of the consecutive ones and consecutive zeros, and in which case we can solve. Of course, we can have self-synchronization, and we can provide good error detection and correction, because we can reduce the baseline wandering and the DC components. So how is the block coding done? It's extremely easy. So the issue is that so the so in the sender side, so what we do is that we take m bits and we convert it to n bits. So here, if we convert m bits to n bits, then n is greater than m. Okay, so for example, we take four bits and we convert it to 5 bits here. Okay, so with 4 bits, how many combinations we have for 4 bits, ya shabab? How many combinations do we have for 4 bits? 16. Okay, so how many combinations do we have for 5 bits? Tamam. So of course we have with 32-bit combinations, we have more degrees of freedom, right? So we can use 16 bits out of the 32, 16 combinations out of the 32, with some transitions between the ones and zeros, right? And remove the ones that have 5 zeros or 5 ones. واضح كده؟ So this is the main idea really, is to do the substitution for each m bits with such that in m أكبر من m. There is no يعني place for equality here. If m equals to n, we cannot do that because if m equals to n, we have the same number of combinations at the input and at the output. So we don't have any degrees of freedom, in which case the line coding, the block coding will not work, right? So that's the idea. So here we have at the transmitter side, at the sender side, we have each 4 bits will be converted to 5 bits. And of course, in that, we will select the combinations out of the 32 combinations for the 5 bits that have more transition between the ones and the zero. And then apply by the non-zero, non-return to zero line coding, as we normally did before. The line coding, the non-return to zero line coding, as we said before, it has some advantages. If you remember, the bandwidth or the signal rate was actually n/2, which is the limit. So the bandwidth is low and it's simple. Okay. However, we had the problem of consecutive ones and consecutive zeros, and this causes the baseline wandering, DC component, and lack of self-synchronization. So by introducing the line coding, we can solve all these problems. So we can have transitions between the ones and zeros before we apply the non-return to zero. In that case, of course, we can avoid all these problems. The way that we do this is by saying, okay, so now we have, this is the input. This is all the possible input that we have for 4 bits, right? So if we take each 4 bits of the input sequence, then these are all the possible combinations that we have. And as you can see, when we convert this to 5 bits, the number of transitions between the ones and zeros in here is definitely more than here. Okay, so for example, how many transitions do we have in this 4 bits? How many changes do we have in this 4 bits? Changes from 0 to 1 or from 1 to 0, yani. So how many changes do we have here? 0 بالظبط. Yes, so 0 because we have from here to here we don't have a change, from here to here we don't have a change, from here to here we don't have a change, right? So how many changes do we have here? We have only one change from this one to the 0. So we have introduced one extra change. So if we talk about this, also we have here number of changes is 1, صح? And here the number of changes is A. So we have 1 change, 2 change, 3 change. Okay? So here, for example, we have 1, 2, and here we have 1, 2, 3. Okay? So you always have more changes here more than here. Okay? So this way we can have more transitions between the 0 and 1 and the 1 to 0 and the 1 and 0, so that we can avoid all the problems that we talked about. Of course, with, as I said, with 5 bits, we have 32-bit combinations. We took already, these are 16 combinations, and we are left with some other combinations, extra combinations. So for example, the straight zeros, we have the 5 zeros, of course, because we cannot use them for data, and we have 5 ones, and we have all these combinations are still left to be used. So what we do is that we use these combinations as control signals. These are control signals. Okay, so we use them locally between the physical layer and the data link layer to provide something. For example, we have mentioned to you in network 1 that we can use, for example, the start delimiter to mark the beginning of a frame, and the end delimiter to mark the end of a frame, right? So we can use these combinations as control signals between the physical layer and the data link layer. And in the data link layer, we are sure that we cannot have these sequences as part of the data by any means, because we have already you replaced all the other combinations with the data. So we cannot have these sequences as part of the data anyway. واضح يا شباب? So this is simply the line coding techniques. And the good thing about line coding here is that it's agnostic to whatever line coding technique we use. So we introduced the block coding, and then we can use non-return to 0. We can use any other line coding technique that we have studied, and they are orthogonal to each other. So there is no actually effect from one over the other, except that by introducing more changes using block coding, we can use a more simpler line coding technique like non-return to 0, in which case we can solve the problems of lack of self-synchronization and the error improvement by using the block coding technique. So this is the so forget about this crosses of lines. Sometimes they use block coding together with some scrambling. So forget about this. We don't have to worry about this. But the most important thing is that each 4 bits will get converted to 5 bits. Okay, so this is the main idea, and by doing this, we add more transitions at the output sequence. One thing to notice here is that so nothing comes for free, as we said before. This is the general rule. So what is the cost of block coding? What is the cost of block coding based on which we have improved the self-synchronization and the error probability? What is the cost that we had to pay here? Yes, Daniel. Yeah, so it's overhead, right? So block coding introduces a overhead. Okay, so I had to add extra bits, which will effectively affect the bandwidth that I need, or I have to reduce the overall bit rate in order to use the same bandwidth. So block coding introduces overhead. So for example, what is the overhead if I use 4 to 5? If I use 4 bits to 5 bits, then I have actually added 1 bit, okay, to every 4 bits. So it's actually 25% overhead, right? So I added 1 extra bit for each 4 bit, which means that the overhead that I added is actually a 25%. This is the block coding, and in practice, of course, sometimes they use smaller block coding circuits, okay, to implement a bigger block code technique. So, for example, if I want to convert 4 bits to 10 bits, right? So in that case, I can actually use 4 bits to 5 bits, okay, block, and then I use 2 of these. So this is 4 bits to 5 bits, okay, and I put them in one box, and I put the input. So this way I can convert each 8 bits to 10 bits. This is equivalent to this, of course. So if I have a block of 5 bits to convert to 6 bits, and another one 3 to 4, then essentially I have in total 8 to 10. So this way I can actually have a bigger block coding circuit using smaller block coding circuits or chips. Yes, Daniel. Mm-hmm. Mm-hmm. It is 2 blocks. If you apply them sequentially, then it's okay. But if you apply them parallel, then the input must be 8 bits. So you take each 8 bits of the input sequence and you convert it to 10 bits at the output sequence. Yeah. Of course, they are. Yes, they have to work together. So the good thing about this as well is that they can introduce the disparity controller. This disparity controller, you don't have to worry about it so much, but this actually introduces the concept of inversion. We have talked about the concept of inversion before, if you remember. The concept of inversion sometimes improves the error, the error correction or the error detection by having to balance the number of ones and the number of zeros, the number of positive voltage and the number of negative voltage. So if you have positive voltage similar to the negative voltage, then you have balance, and you can introduce the baseline wandering, or you can improve the baseline wandering, in which case you improve the error detection. So as we have talked about in other line coding techniques, if I find that the number of positive voltages is actually more than the number of negative voltage, the next sequence can be inverted. The next sequence can be inverted such that we introduce more negative voltage more than the positive voltage, in which case we balance and we keep the baseline exactly in the middle. So this way we improve the error quality. So this disparity controller introduces the concept of inversion, similar to what we have done for the multi-level technique with 4 voltage levels, if you remember. In any case, this disparity controller is optional, and sometimes it gets added to improve the detection. So this is as far as block coding. So block coding, as I said before, it gets introduced complementary to the line coding scheme, okay, which definitely adds some overhead, okay. By adding this overhead, we can avoid the consecutive ones and the consecutive 0, in which case we improve the lack of self-synchronization and we improve the error detection. So the motivation of scrambling the motivation of scrambling is to try to do the same objectives similar to block coding. However, in this case, without adding any overhead, without adding extra block, or extra overhead. So in that case, instead of introducing this substitution stage from 4 bits to 5 bits or whatever, we will try to change or modify the line coding scheme itself, okay, to avoid the consecutive ones and the consecutive zeros, okay? So we have to do it based on the line coding scheme, which means that here we have to get inside how the line coding scheme actually works and modify that, tweak this. واضح يا شباب؟ So block coding did not have to do that. Block coding is complementary, it's separate, and it's actually agnostic to whatever line coding technique we use. We introduce block coding at the beginning and that's it. Then we use any simple line coding technique. Here, we have to do it built in. We have to modify the actual line coding scheme, okay, in order to scramble the voltage levels in such a way that that tells that allows the receiver to have self-synchronization for the clock. It allows the receiver to improve the error detection, but without adding any overhead, okay? And as we will see, in all cases, this always comes with a cost. Nothing comes for free. So for AMI, the logic was as follows. So if you have AMI, if you have a sequence like this, 0, 0, 0, and then 1, 1, 1, مثلا. So the 0 is simple. 0 is simple. So 0 is 0 voltage. Okay. For the 1, the first one, if the first one is positive, the second one is negative, and then positive. That's why it's called a AMI, alternate mark inversion, or alternate mark inversion. So that's the sequence of AMI. So obviously, for the case of consecutive ones, we don't have any issue, right? It's clear that for the case of consecutive ones, we don't seem to have any issue. We have alternation between positive voltage and negative voltage, and this alternation is actually good because it helps us to have baseline, to improve the baseline wandering, to improve the DC component. In fact, one of the biggest advantages of AMI is that it has no DC component at all. Why? Because for consecutive ones, we have alternation. For consecutive zeros, we have fixed voltage. However, this fixed voltage is with zero power, right? So fixed voltage means zero frequency, right? But this has zero power. So we do not have any DC component, right? So, so AMI has the issue of baseline wandering for the case of consecutive zeros, okay? And it has lack of self-synchronization again for the case of consecutive zeros. In other words, the main problem and the only problem with AMI is the consecutive zeros, right? Consecutive ones are no problem whatsoever. The problem is with consecutive zeros. So, okay, so the problem now is clear. So let's take the consecutive zero sequence and try to do something with it, try to tweak it a little bit, right? And remember, we need to do this tweaking in such a way that we do not add any overhead. We do not add any overhead, okay? To do this is that we will study the scrambling for AMI. Remember, for AMI, do this. So we will study two techniques. This is number one. This is the one that's used in North America. It's called B8ZS. And remember here, all line coding techniques, they do not have slashes in the middle. If we have slash in the middle, then we talk about block coding. عشان بس إيه, in terms of convention for the naming convention for the different line coding techniques. If you have slash in the middle, this indicates block coding, right? If you have no slashes in the middle, this means that this is a line coding technique name. So the B8ZS technique, as I said, this is the one that's used in North America. So the logic for this scrambling technique is very easy. So we will look at the input sequence, and then we will try to identify 8 consecutive zeros. 8 consecutive zeros, right? So for the 8 consecutive zeros, we will kick the scrambling technique B8ZS. If you have 7, we don't do anything. Remember. So for 7 zeros, we don't do anything. Only when we have 8 bits, 8 consecutive 0 bits. And the idea here is that assume that we have 1 here, right? So 1 is the positive voltage, okay? And we have 8 consecutive zeros. So in the normal AMI sequence, these 8 consecutive zeros will be like this, right? It will be a straight 0 voltage for all the 8 bits, okay? So instead, what we will do is that we will replace the 8 bits as follows. First, the first 3 0 will have 0 voltage, and then we will add, or we will replace the 4th voltage level with something called violate. This is called a violate. Why is it called violate? Because if you look at this voltage level, you will see that this is similar to the voltage level of the one before it. Okay, so what is the normal logic for AMI if this bit is 1? The normal logic for AMI is that this voltage, this one, will have to be negative, right? So this is violate, which means that it violates intentionally, it violates the logic of AMI to tell the receiver that pay attention to the fact that this is not the normal logic for AMI, in which case this bit is not actually 0. This is scrambling. This is scrambling. So by introducing the violate, we tell the receiver that this is not in fact 1, because if it's 1, the voltage level would be negative, not positive. So the violation here comes intentionally to introduce more alternation in the voltage level. Okay, so we put violate and we put bipolar. Bipolar here always is the opposite voltage of this. So bipolar here means that if this previous one is positive, it comes negative. If it's negative, it becomes positive, like here. Okay, and then 0, and then we violate again. Okay, so violate, B, 0, violate, and then B. Okay, so all these 5 consecutive 0 bits have been replaced or have been tweaked into different alternations of zeros and positive voltage and negative voltage. And as you can see, by introducing these alternations here, 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 and here, and here, of course, these alternations will improve significantly the baseline wandering and the self-synchronization, because we don't have the DC components anyway in AMI. So in which case it will improve the error quality and the self-synchronization feature. So if the first one was actually negative, okay, then again the substitution is the same: 0, 0, 0, and then violate, which means that this voltage level will be similar to this, and then bipolar, which means that we go negative polarity, the opposite polarity, and then 0 stays 0, and then violate again, which means that this voltage will be similar to this, okay, and then bipolar. So it's 0, 0, 0, VB, 0, VB, okay? And as you can see, we have introduced two transitions and two transitions to balance out the positive voltage and the negative voltage, which also improves the baseline to be around the middle. Okay, so not only did we introduce transitions, we have actually balanced the positive and the negative voltage, and this has good implications on the baseline wandering and the self-synchronization. Okay, so this is the concept that's used in North America. In Europe, they tried to do the same technique, more conservative approach. So in B8ZS, what we try to do is to replace each 8 zeros with 0, 0, 0, and then VB, 0, VB. In Europe, they use HDB3, and in HDB3, they try to replace each 4 bits, each 4 consecutive zeros, not 8, each 4 consecutive zeros. And the idea is simple. Again, it's pretty much the same. So we substitute each 4 zeros, okay, by a sequence. But here we have two cases. We have 1 and 2. So if we have number of non-zero before this substitution, if we have number of non-zero that's odd, okay, then we use that substitution. If it's even, we use that substitution. Okay, and as you can see here, it's odd. So we have one transition. So if it's odd, we introduce odd. Odd plus odd is even, right? And for case one, for example, is here. So case one is here. So if we have number of ones before that substitution, okay, that's odd. So of course here we have only one, okay. Then the substitution will be 0, 0, 0, V. And as you can see, V here is the same like this voltage level, exactly the same. Okay, so if this one is negative, the V will be also negative. So this is the concept of violate. Okay, so if we have even number of ones, like for example here and here, right? Because here we have what is the number of ones before this substitution, ya shabab? What is the number of ones here before this substitution? Just to confirm whether you are focusing or not. Sulaiman, what is the number of ones before this substitution, ya Sulaiman? It's a? لا, the number of ones before this substitution here. Here. What is the number of ones here? There's no number of, there's no ones. So the number of ones, yeah, between the second substitution and the third substitution, the number of ones is actually 0. Okay, so for us, of course, 0 is even. 0 is even. So we trigger the second case and we do B 0 0 V. Okay, so B here means that we go opposite to the last voltage level, which in that case it was negative, so we put it positive, and then we put 0 0 and then violate, which means that the voltage level will be exactly the same like the previous non-zero voltage. Okay, so violate always means that the voltage level will be the same like the non-zero voltage before it. So if it's positive, it comes violate is positive. If it's negative, violate is also negative. Okay. Okay, so for the HDB3, we have we try to be more conservative to replace each 4 consecutive zeros. Okay, and we have two cases. If the number of these 4 consecutive zeros, if the number of ones before it is even, then we replace the 4 zeros with B00V. If the number of ones before the consecutive 0 bits is actually odd, okay, then we replace it with 000V. Okay, so this is the scrambling technique, and as you can see here, we did not introduce any overhead in terms of bits. Yani, we did not add any bits, we did not add any extra bits, we did not add any extra blocks, right? So we have to get into the how the line coding scheme works and modify that, tweak that to try to introduce more voltage transitions, which will allow us to have self-synchronization and improve the baseline wandering. Type. Again, does this come for free? What is the cost that I had to pay here? What is the cost that I had to pay? فين يا شباب؟ فين الانتراكشن؟ الناس نايمة ليه؟ What is the cost that I had to pay? هو overhead in terms of what? Overhead not by adding extra bits here. هو overhead جاي من ال complexity of the sender and the complexity of the receiver. This is there is a complicated logic, right? So definitely we had to complicate the logic of AMI to introduce scrambling, right? So we had to complicate. So we have to find all the consecutive zeros, and we have to replace the consecutive zeros with 0, violate, bipolar, things like that. So that adds some complexity at the sender and at the receiver to try to detect that at the receiver side. Yes, Daniel. Right, right. So this, yes. So that's what I'm saying. So when you find the violate, then you have a very complicated logic. So we have to go back, because we know that violate for this technique is triggers a replacement for 4 consecutive zeros. So the 4 consecutive zeros, we have to go back and find all the 4 bits to convert them to 0. So what you are saying is actually a very good observation, that now the receiver has to go back and forth in order to decode the bits, whether they are ones or zeros, right? So if it finds that this is B, so logically it may say, oh, okay, so this bit is 1. صح? This is a very nice observation. But then it finds 0, 0, and then V. Once it finds the V, then it has to go back 4 bits and say, no. This was not 1, because I have V here. So this was actually, in fact, also 0, because V means that I need to replace 4 consecutive 0 bits. Okay, that's why I said this logic is more complicated. So so the receiver doesn't have to, the receiver doesn't only need to look at the current voltage level. It needs to go back in many cases to replace the voltage levels to ones or zeros. It may have to go back. واضح كده؟ So any questions with this? So again, so just to summarize, in this chapter, we talked about digital transmission, where we take the digital signal after converting the bits into signal, into a digital signal. We transfer the digital signal as is on the line. So with this, we have discussed some issues related to the consecutive ones and the consecutive zeros. So we have talked about many line coding techniques that each one has some pros and cons, and we have been able to analyze the performance of this line coding techniques using the signal rate and the bandwidth. We have been trying to identify whether this line coding scheme has baseline wandering, it has DC component, it has self-synchronization or not. And we have categorized the line coding schemes into 5 main categories: the unipolar, the polar, which uses positive and negative, bipolar uses positive, negative, and zero, and then the multi-level, which we can replace more than one bit with one voltage level. So we have multi-level, and then the multi-transition, where we can have the transitions between the voltage levels to indicate the zeros and ones. So that was part 1 of that chapter. Part 2, we have talked about block coding. And block coding gets introduced before line coding techniques to improve the self-synchronization and the error detection. And we do this by adding extra bits to the input bits to try to have more degrees of freedom to avoid the consecutive ones and the consecutive zeros. By doing this, we can simply use any simple line coding technique, and we are guaranteed that we will not have the consecutive ones and the consecutive zeros, which tend to cause all the problems that we talked about. And then we talked about scrambling techniques, where we try to do the same objective, but without having to add extra bits or without having to add extra blocks. In that case, we had to go into the line coding scheme itself, and we had to do the concept of violation and bipolar, and we use the substitution for consecutive 8 zeros or consecutive 4 zeros, right? So that's this is the part that was missing in chapter 4, and so we can switch to chapter 11 now and start